Hello fellow skeptics, I'm Luther Name, and this is the 18th video in a series addressing the broad topic of, is something wrong with modern physics? If so, what? And can it be fixed? Now, in the prior two videos I discussed special relativity, which had been renamed the restricted theory because Einstein moved forward in what he perceived as a more general theory, and that general theory of relativity subsumed the restricted theory as a component. Now, this particular video, it gave me some problems, not because the topic was difficult, but for other reasons that were not obvious, perhaps more personal. And I'll get into that as we go along. The problem, as I saw it, was there's nothing wrong with Einstein's equation, a general relativistic equation. When you look through it and you see how he derived it, and I'm not sure that he actually derived it, I don't know how much he actually contributed, because I believe it was Marcel Grossman, a mathematician he worked with, whom I suspect was the one who gave form to it, with Einstein urging him to help develop an equation that was a generalization of the Euler-Lagrange equation itself. The Euler-Lagrange equation had been developed initially back in the mid 1700s as a geometric equation by Euler, one of the pioneers in that area, and it was a mathematical technique for finding shortest paths between 2 points in particular kinds of environments, described by the coordinate system used to describe those environments. Like on a surface of a sphere, you have a particular coordinate system. On a cylinder, you have a coordinate system for that. In flat space, well, we have basically x, y, and z, or after Minkowski, we have x, y, z, and time. So we have 4 dimensions. And so the Euler-Lagrange equation describes trajectories and paths, shortest paths, in these particular environments. Lagrange adapted some of these principles and the evolving calculus in the late 1700s in reformulating mechanics and dynamics that Newton had begun to develop himself using his graphic techniques and the very early forms of calculus, or what became known as calculus. This evolution occurred further into the early 1800s. Hamilton reformulated even Lagrange's approach to mechanics, and in fact gave form to what we call the Lagrangian, which is nothing more than the kinetic energy minus the potential energy. The concept of potential energy was best evolving in the early 1800s, and so Hamilton identified a quantity he called L for Lagrangian, which was equal to the kinetic energy of an object in a system minus its potential energy in that system. And so he applied that in the Euler-Lagrange equation and identified then a set of dynamics that could be, and we have used it since that time for finding orbits in standard Euclidean space, which is x, y, z, that we're all familiar with. But Einstein had understood, because of the nature of the 4-vector, the Minkowski 4-vector, which became known as the Lorentz metric, it defined a new space. And you could apply the Euler-Lagrange equation to it, but his intention was to do similar to what Newton had tried, which was you have a first principle and then to generalize it. And what he was after was generalizing the Euler-Lagrange equation to not only 4 dimensions, but any dimension. And so he worked with Marcel Grossman, and Marcel Grossman was a mathematician who may very well have been the total architect of the equation. He came up with a tensor form for the Euler-Lagrange equation, and he also created a tensor description of the Lagrangian, so that he now had a generalized formulation of the Euler-Lagrange equation that would reduce, using the algebra and calculus associated with tensor analysis, which would reduce to the standard Euler-Lagrange equation that most of us know. Now, the difficulty that I ran into was I didn't really know how to talk about it, because there's nothing wrong with that equation. What's wrong with general relativity is the metric that they use, the spatial descriptions that they plug into it. The equation itself is quite good. In fact, it's extraordinarily complicated. Those of us, at least me, in order to convince myself that I was on the path towards understanding the tensor descriptions of the thing, which was generalized, I then picked an example and reduced it to something that we already worked in directly from the Euler-Lagrange equation. And the tensor equation, in fact, reduces to that equation. So it gives you confidence that you understand how to manipulate it. But it's an extraordinarily difficult equation to work with. In fact, what is not normally appreciated is that Einstein's didn't think anybody could could use it. He was surprised how quickly, I believe it was Schwarzschild, came up with an actual solution to it. Perhaps apocryphally, but his comment was, I didn't think anybody could solve it. So it was a general equation. And in that sense, it wasn't the physics. It was math. It was similar to the Newtonian approach of developing calculus. Calculus was a tool to help him do physics. In Einstein's case, it became a tool that he never really used directly. I find almost no indication that Einstein himself was comfortable working with that general relativistic equation of his. Now, the equation's good. It works fine. But we put the wrong stuff in it. The equation may be good. It's like Newtonian mechanics. It's very straightforward. The Euler-Lagrange equation, we use it making orbits, describing orbits and paths in the presence of gravity or mass. But if you have the wrong forms, if you don't describe the kinetic energy correctly, if you don't describe the potential energy correctly, if you don't describe the dynamics associated with it correctly, then you get a garbage answer. The equation's perfectly good, and the answer is good for the garbage that you put into it. That's the problem with general relativity. We're putting garbage into a perfectly good equation. Now, the difficulty I ran into is that it's so difficult to work with that my approach in this series of videos, which has been to provide a roadmap, a guidance, mostly identifying misphysics or misapplied physics. But in this particular instance, it's so specialized that it may be good guidance, but all I can hope for is that people will dispense with the use of this Minkowski reformulation, the Lorentz metric, and this idea of space-time, and work with a different set of coordinate systems. Now, that was one of the issues. The other issue was that general relativity has been nicely described as it is in a multitude of presentations. You can go onto YouTube and you can find some that are very good. These have been described through a series like Nova on PBS and a multitude of others. Very good graphics. And so everybody kind of has a general feel for what general relativity is supposed to be describing and how it's supposed to be working. The interesting thing is that every description that's used for general relativity holds equally well for regular Euler-Lagrange solutions or equations. It's the same equation. And so the descriptions, while they seem specialized to general relativity, they're perfectly valid for regular kind of Euler-Lagrange equations of motion that we use and the dynamics that we use the equation to match. So what we've done is we've created a specialized vocabulary. We've got people who are very specialized in working with this equation, and the results are garbage because it's like we all know with the computer, garbage in, garbage out. The equation's good. The solutions are very poor. So what I'm going to try and do here is to convey a sense of where we should go in using the general relativity, the equations that Einstein derived, where they came from and some of the evolution. But given the very high quality of so many of the videos and presentations and programs that have appeared over the years on general relativity, I can't improve upon that. I wouldn't even try. They're still valid, and I have to admit that I find that the way of looking at general relativity from the gravitational distortion of space is kind of satisfying. It answers certain questions. It allows us to, or allows me anyway, to feel more comfortable with what we're trying to describe that is occurring, as opposed to the standard approach, which is, well, the propagation of gravitational force propagating at the speed of light, as opposed to what we're talking about is just a distortion, changing the metric and the shape of the space associated with the presence of mass in that space. I find that to be a very good description. So I found it a little difficult to kind of come up with a way of continuing with the basic theme of these videos, which is to supply a roadmap. And the other thing, which was not too obvious, was the more I got into it, the more irritated I got. I got irritated because as I was watching a variety of videos and people describe what's going on, I kept running through my mind saying, well, this is like Back to the Future or Deja Vu all over again. You know, this is the kind of stuff we went through starting with Newton. And that is, it was incomplete. He did what he could at the time, and he made approximations, and then once those approximations were made, we walked away from the background, understanding the background of what those approximations were, and we continued to use, for instance, the inverse square point mass approach to gravity. Now it works pretty well, but it's not academically sound. What have we done with general relativity? The same thing. As it stands at this point, the metric we put in there, well, first of all, we use point masses. Well, therefore it's an approximation right off the bat. Because as I showed in the early videos on Newtonian physics, Newton described what he was trying to do, but he couldn't do it. And in fact, up until the era of computers, we couldn't do it very well, or only with difficulty, and so nobody even tried to do the actual solution to the Newtonian approach to the attraction associated with gravity. So what we have here in the modern era, we could do better. And I see the presentations, and they're all very good, and they're very persuasive. And I'll pick an example, and I don't mean to pick on him, but Sean Carroll, who has been a general contributor in this whole area of cosmology and the equations that are satisfactory. He says, and he comes out, and he's just one of many. He says, physics is in trouble. For the last 40 years, we've made no progress. Well, duh. And I say to myself, yeah, but you're part of the problem. I don't need you to tell me that there's a problem. I need for you, with all your vast experience, to help us understand what the problem is, why it exists, and how we get around it, or how we come to a solution, or to identify exactly what went wrong. You know, it's kind of ironic. Sean Carroll, his namesake Lewis Carroll, had a kind of a fantasy world, and so many of the academics actually live in this fantasy world. And my irritation was, don't talk about it, do something about it. But they're locked into a particular point of view, and they can't get out of it. And I'm quite afraid that, much like Planck, Nobel laureate Planck in 1900 stated, the only way many ideas change is if the people who believe in them disappear. They die, and new people come in who are more comfortable speaking things. The old guard simply can't adapt to a new way of thinking. And that's what I'm thinking is going on here with academia. I'm not sure you can get there from here. But that's beside the point. Let's stick to general relativity itself. So what I'm going to do is I'm going to emphasize some of these points that I've just spoken about with some graphics, not many. They're far too complicated to get into, and this is not a primer on tensor analysis and working with a general relativistic equation. Just to re-emphasize that point, Einstein had a famous 1916 paper where he introduced the broad topic of general relativity and his equations. What's interesting is that paper is a teaching paper. What he did was, he didn't do much physics. I don't think he did any physics. He did a development of the equation. It was a primer. It was a paper to be read by people who were not, physicists in particular, who were not familiar with advanced mathematical concepts like tensors. And so he went through a derivation or a process. He didn't solve any problems at that particular point. And if you fast forward into from that era into the era when I was in university, my textbook, a well-regarded textbook at the time, if you look at it, it's a paraphrasing of the content of that 1960 paper, teaching us how to use and develop the equation associated with general relativity. And of course the examples that they apply in helping us understand it are basically Newtonian, Euler-Lagrange types of equations. So it's a topic that almost all physicists are exposed to. They don't work in it. Those few that do work in it have drifted off into kind of a neverland where it's all hypotheses, things that can't be measured, things that can't be proved. And now, as we have our telescopes, these fantastic pieces of equipment that are in orbit, we're seeing physics that we don't understand. We're seeing things that we don't know why they exist. We can't even interpret them. We don't have the mathematical and physical foundation to even understand what we're seeing. We've got a problem. Houston, we have a problem. Well, what's your problem? Well, gee, we're not really sure. But nothing seems to fit. And we're going to have to come up with some new physics. Well, what have we been doing for the last 40 years since you've known that something has been going wrong and the physics has been, academic physics at least, has been going off the rails? I'm going to stop this video at this point before I get into the viewing materials. I said before that I wasn't going to delve into the details of Einstein's general relativistic equation, but as I was preparing the visuals for this particular video, it occurred to me that in fact I can and I should, because the overall goal of this particular set of videos is to provide a roadmap, a way in which we can move forward, fix what may be broken. And what I did was note that in our very early videos in this series, I in fact identified ways in which we can move Einstein's general relativistic equation from being an approximation, which is, even though the equation itself is exact, we put the wrong stuff in it. Garbage in, garbage out. And so what I want to do is talk more about that, little tutorial, small, short, and then how we can go ahead and use his general relativistic equation and some of the attributes of it that don't seem to be obvious to people who are using it. So with that, I'm going to stop at this point. I'm Luther Name. Leave a comment if you would, and I'll continue with the general relativistic equation, how to fix it, in the next video.